Good evening, ma'am. Our group name is ABC and our assignment is Tower of Hanoi. Here comes the problem statement. It's a classical mathematical puzzle and it's often used for the teaching recession and problem solving strategies. And here comes the components. There will be three rods like three pegs and source, auxiliary and the destination peg. A number of discs are of different sizes. All discs start stacked on the source peg. They are arranged in increasing order from top to bottom. This means smallest on the top and the largest at the bottom. Basically, the goal of the puzzle is to move the entire stack of the discs from one source peg to the destination peg, following some rules. The rules are as follows. Only one disk can be moved at a time. You cannot move multiple disks together. A move means taking top disk from one peg, placing it on the other peg. No larger disk can be placed on top of the smaller disk. This prevents breaking the order. Finally, the puzzle is important because it demonstrates precision problem solving. For n disks, the minimum number of moves required is 2 power n minus 1.
State space representation. State space search is a problem solving approach in artificial intelligence. A problem is represented a set of states. The initial state here is where the problem starts. The goal state is a solution we want to reach. Actions are legal movements that describe how we can move from one state to another. The state space is the collection of all possible states and their connections. A search algorithm then used to explore this space to find out a path from initial state to the goal state. Here is a state diagram of Tower of Hanoi problem. Each node in the diagram represents a particular configuration of the disks on the three pegs. We begin at the initial state where all disks are stacked on the first peg. From here, arrows represent the possible legal moves, which involves transferring the top disk from one peg to another peg without replacing a larger disk on the top of smaller one. As we follow these arrows here, we move through a sequence of intermediate states that shows partial progress towards the solution. And finally, we reach the goal state where all disks are successfully transferred from one state to the third state. The representation is useful because it allows us to apply search algorithm from the start state to the goal state and analyze their efficiencies.
So, as part of search techniques, we implemented BFS and hill climbing techniques. BFS explores the states level by level using a queue, and it ensures the optimal solution would be found. We avoid revisiting states by keeping track of already explored configurations, and the reference code is here. We have the start state and the goal state. Start state is every state is a tuple of three pegs, and each peg consists of the disks. So the start state configuration is on first peg we have 3 to 1. So the disk 3 represents the largest disk and 2 is the medium sized, 1 is the smallest size disk. So the goal is to move all the stack of disks to the goal peg, that is peg C. So we call the BFS algorithm. It takes two parameters, start state and goal state. We initialized a DQ and we push the start state, and the second parameter represents the solution path, and we are maintaining a visited set to keep track of all the visited configurations. And while queue is not empty, we are popping the leftmost element from the queue, and if the state is equal to the goal state, then we are returning the path stored till now. Otherwise, we'll get the neighbors for the current state, and so we call the get neighbors to generate all the neighbors for the current state. Okay, so get neighbors, we initialized a neighbors list to store all the possible moves from the current state. So the pig so the pig stores the current state, and this part of logic, what it does was, uh, it goes to every pig and removes the top disk from that pig and tries to keep it on other two pigs, by following the rules. That is, the smallest disk can only be placed on the largest disk. So we try for all the three pigs, and if that pig is not empty, then we are taking the top disk. And so this part of loop checks all other pigs whether we can place it or not. So if I not equal to j, it represents, if it is not its original pig, then we'll go and check if this disk is less than the top disk placed on the pig j. If it is, then we remove this disk from the ith pig and append it to the jth pig. Then we will add it to the neighbors. So at last, this function returns all its neighbors, all the neighbors of the current state. Um, okay, so for every neighbors we'll get from the get neighbors function, we'll see if that neighbor is not visited, then we will add it to the visited set and we will add it to the queue. And in the path we will add this neighbor also. So at last, this loop breaks when the queue is empty or if the goal state is found. Otherwise, we return none, representing that we didn't find the goal state. So we'll get the solution path. Then here we are printing the number of moves taken to find the solution, and this part of code prints the solution path. Otherwise, if the BFS returns none, that means we couldn't find the solution. So we are printing that as well. The output we got. So the BFS solution, so the BFS algorithm found the solution in 7 moves, and this is the path. This is our start state, and then it went to all these states, and we have achieved the goal state. That's it. So the uninformed search BFS is over. Then hill climbing, we also implemented hill climbing technique. It uses a heuristic function. So the heuristic function we used here is number of disks correctly placed on the goal peg from the top, and the algorithms moves to the neighbors which has the better heuristic value than the current state. It is possible that it may get stuck in local maxima or if there are some plateaus, and the reference code is here. So this is our start state and this is the goal state. So we are calling hill climbing function. It takes the start state and goal state as its parameters. So our current state will be holding the start state, and we will add this current state to our path. Then this part of while loop continues until the current state is not equal to goal. Then we'll get all the neighbors from the current state. As I explained earlier, this get neighbors function will gives all the possible states from the current state. Then we'll get the neighbors from the get neighbors function. If there are no neighbors, then that means we have reached our maximum, so we'll break out of the loop. Otherwise, we'll so this part of code gives the neighbor with maximum heuristic value, then that would be our next state. And we will check the heuristic of the next state and the heuristic value of the current state. If it is lesser, if the heuristic value of next state is less than the current state, that means we have reached the local maxima or global maxima. Then we break out of the loop. Otherwise, next state becomes our current state, and then we will add this current state to our path. At last, when all these conditions met, we'll return the path. So it is possible that hill climbing won't find the optimal solution or the complete solution. So it is an incomplete algorithm because of the local maxima or some plateaus. So because of those reasons, it won't give the complete solution. I will run the code. So here we can see that we couldn't find the solution using hill climbing. It stopped in the second move itself because of the local maxima. Because of the local maxima problem, it might be possible that after this state, the heuristic value of this state and its neighbor values would be lesser. The neighbor values, heuristic values, might be lesser than this state. That's why this algorithm stopped. Okay, that is for coding part. And coming to the performance analysis for the BFS, the time complexity is b power d, because in the worst case we are exploring every state level by level. So if b is the branching factor and d is the depth, then the time complexity would be b power d, because at the worst we might have to visit all the b power d states. And space complexity, as we are maintaining a queue, the space complexity would be b power d, all the possible states. And the completeness, BFS always, it ensures that it finds a solution, like optimal solution if it exists. Then optimality, it guarantees the shortest path as it is exploring the nodes level by level. And the limitation for the BFS is it is too much of memory intense, and it is slow for deep problems as time complexity is p power d, because it has to explore every other nodes. Like here in b power d states, it has to explore. And performance analysis for hill climbing, the time complexity is b power m. B is the branching factor and m is depth. And space complexity is order of b, because we move in a greedy manner. We'll move according to the local maximum, like local optimal one. So the space complexity, at a time we will only move in one direction, so the space complexity would be order of b. And the completeness is not guaranteed, because it might get stuck because of the local maxima or plateaus. And the optimality, it won't guarantee that it will find optimal solution, as we have found in the sample run of code as well, because of the local maxima or the plateaus exist in this hill climbing algorithm. And the advantage of this algorithm is it is very much memory efficient, as it won't store every possible state, because it moves only in one direction, so it might have to store just the solution path. And the limitation for the hill climbing is it is too much dependent on heuristic quality. If heuristic is good, then it will gives us the best solution or the good enough solution. Otherwise, it won't be that efficient.
Now let's compare the two algorithms we applied to the Tower of Hanoi problem, breadth for first search and hill climbing. So BFS has a time complexity of O of b power d and the same order for space complexity, which means it can get very costly in terms of memory. But BFS is both complete and optimal. So if there is a solution, it will definitely find it and it will be the best one. And on other hand, hill climbing is much faster with O of b power m time complexity and O of b space complexity, but it is not complete and not optimal. This means it may fail to find a solution or may give us a suboptimal one. And here are some of the practical observations. So BFS ensures the shortest solution, but it consumes a large amount of memory. And in BFS, each state is treated as a configuration of disk on the pegs, and it systematically generates all valid moves from that state. In climbing, it is much faster but heavily depends on the heuristic we design, and it also uses a greedy approach which picks up the move that seems to give an immediate improvement. Ultimately, the choice of algorithm depends on the size of the problem and the requirements, whether we care more about efficiency or about guaranteed optimality. And so the Tower of Hanoi example is here. So the initial state, it is represented as 3 to 1 in the first peg. That means all the threes in disk in the first peg, and the goal state, which is 3 to 1 on the last peg. So BFS explores the state space level by level, ensuring that it finds the shortest sequence of moves. But hill climbing ensures and it tries to push all the disk towards the goal by using heuristics, which makes it faster but not always reliable. And so to conclude, the Tower of Hanoi problem, it can be solved using very different strategies, but BFS gives the optimal solution and at the cost of memory and time. But hill climbing is more efficient, but it may sometimes fail or end up giving a non-optimal solution. And therefore, the choice of algorithms depends on importance of optimality or efficiency, and the size of the problem as well. And it also depends on whether we have a good heuristic available or not. And so to conclude, this was our Tower of Hanoi problem. And this submission includes all the uh, contents shown below. Thank you.